In this video, I'm going to go through some free body diagrams and net force equations for some common objects moving in a circle type problems. I'm not actually going to go through and do any example problems. We're just going to set up the net force equations and free body diagrams. So first we might have a ball rotating on, let's say, the top of a table, and this is like the top view. Okay. And maybe it's some sort of like motorized thing causing this ball to move in a circle. And of course, it's going to be a frictionless surface to make life easier. Okay. So the ball, if we look at it from the side, is going to have a force of gravity, a normal force, and then it's going to be that applied force or tension force from whatever this thing is. It could be a rod or some sort of stiff string, something along those lines. So we're going to have two net force equations, x and y, but because we are moving in a horizontal surface or circle, the x direction is going to become a centripetal force. So we're going to multiply m times ac here, and then the net force in the y direction is 0, which just shows me that my normal force is equal to Fg. So here, whatever that applied force is, that's going to be set equal to mv squared over r. Okay. Now, sometimes we might be given the constant speed, otherwise we might be told how long it takes to go around in the circle. If we're told how long it takes, that is the period, and that means we need to calculate the speed by doing 2 pi r over the period. And I just want to simplify and show you guys the algebra to simplify this, because right now it might look that the applied force and the radius have an inverse relationship. But when we actually go through and distribute this squared to all the terms, we get 4 pi r squared over t squared over r. So that becomes 4 pi r squared over t squared over r. R cancels. And this actually shows for something moving in a circle, right, if we keep the period the same, but change the radius, that's going to have a direct relationship with whatever that applied force is. So let's say I was able to keep the period the same to go around the circle, but I changed the radius. If I was to decrease the radius, it would decrease the force that that object would need to apply. Now, we don't always necessarily have this type of math. Sometimes we keep the speed the same and change the radius, and if that's the case, we could stay right with this equation. We wouldn't have to do that out for. So the next example is, oops, come on. Okay, we gotta restart OneNote. All right, next example is a car going around a turn. This car is going clockwise. So we're going to have a force of gravity, a normal force, and remember, it's the force of static friction that keeps us moving in the circle here, because we don't want our wheels to slide relative to the surface. We want them nice and stationary relative to the surface, so that's why we use the static friction force. If our wheels are sliding, that means we're skidding, and that means that we have lost control of our car, which is not ideal. So here, it's the static friction force that is going to create the centripetal force. So my static friction force is equal to mv squared over r. And a common question is going to be, what is the maximum speed we can take to go around the circle? So static friction, remember, is coefficient times the normal force. And the normal force, looking at my free body diagram and keeping in mind that my net force is 0 in the y direction, normal force has to equal Fg. So I can plug in mg, mv squared over r. My mass cancels. So what this actually means is, in terms of the kind of basic physics we do, the mass of the vehicle is not going to matter when it comes to figuring out the maximum speed we can take when traveling around a circle. So that's an interesting thing to keep in mind, because mass cancels out of the equation. And none of these things here are based on the mass. The coefficient's based on the surface, not the mass. G is based on the planet we're on. And then R is just based on our turn. None of those things are based on mass. So Vmax, not based on mass. Another common friction problem that we'll see a lot is like a coin on a turntable. Okay? This is another example where we will have a force of static friction creating that centripetal force, because we don't want the coin to slide off the rotating platform. We want it to stay right where it is, stationary relative to the platform surface. So again, we would have a static friction force creating our centripetal force. So we would have coefficient times mg, because again, we have a net force of 0 in the y direction. So normal force and mg, or normal force and Fg are equal. Okay, and sometimes we might be asked to find that coefficient. So that would be v squared over gr. Again, not based on mass, mass cancels. So it would be based off of the speed that we're at, g and r. Now, normally when we have objects on a rotating surface like this, all of these objects have the same period, right? So they're all going to take the same amount of time to go one circle around, but they don't all have the same speed because they're moving different radiuses in that same time. So keep that in mind. All right, another question that we often see is kind of based on the amusement park or fair ride called the Gravitron. I'm going to pull up a video of that real quick in case you have no idea what I'm talking about. All right, so here's a video of the Gravitron ride. You get in and the ride is spinning. Now you can't tell that it's spinning because we have no windows or anything, but it's spinning, right? You can see this guy is kind of like able to hold himself up. So it spins really, really fast, and it basically pushes you against the wall. So this is the ride that we're talking about when I say Gravitron. Okay. So we're not standing on the floor, right? What's keeping us moving in a circle here is the force from the wall on us. The force is continually pushing us in a circle. So that force from the wall on us is really a normal force because it is a surface force. Okay? And then we have a force of gravity downward. And there has to be something keeping us from sliding down the wall. And hopefully you are thinking in your head that that must be a friction force. And since we are at rest relative to the wall, it's going to be a static friction force. So here, our net force in the x direction is that centripetal force. And that centripetal force is caused by a normal force. Okay. All right. Now, in the y direction, we know that the force of static friction has to equal the force of gravity. So let's say the question asked me, what is the coefficient of static friction here? Well, the force of static friction is the coefficient times the normal force. Force of gravity is mg. So I need to substitute in for the normal force. Now, I'm very used to substituting in mg for the normal force. That's not the case here. The normal force is instead mv squared over r. Our mass cancels. We get a coefficient of friction equaling to rg over v squared. Now, it's a good thing mass cancels because this ride works no matter your mass, right? Like, no matter the people here, we got kids, we had that one guy who's an adult. Right? The reason why this works is because mass cancels. It's just the coefficient that matters. So we don't want to go on this ride with like a nice silky shirt. We want to go on with maybe like a cotton shirt, something that'll have a good coefficient of friction relative to the side of the wall. And then the last problem we're going to go over is a system question with circular motion. So here we have a ball that's being spun on top of a tabletop. And that ball is spinning in a circle because there is some sort of hanging mass down here. So basically I've started this mass spinning in a circle, of course, frictionless surface, and it's going to continue spinning in a circle at that specific radius because of this hanging mass here. So acting on that mass m, we have a tension force, a force of gravity, and a normal force. And then acting on this 3m mass, I have a force of gravity, which is going to equal 3 mg. Right, and this Fg is going to equal mg. And I have a tension. Now in this situation, this object is moving in a circle, but this object is at rest. So my net force here in the y direction is 0, which tells me that my tension force is 3 mg, which is good because then that means my tension force here is also 3 mg because it's the same string. So in the x direction, we have a net centripetal force caused by that tension force. So my tension force is mv squared over r. We just talked about how tension is 3 mg. Okay, so my mass cancels, right? So 3g is v squared over r, which is that centripetal acceleration. So this object actually is feeling an acceleration 3 times the acceleration due to gravity, which is pretty intense. So that's kind of interesting. Maybe I used too big of numbers. But yeah, that's how we would do this sort of system equation. Not much different than what we would do in general. And that is about it for objects moving in a horizontal circle.